Folks, we're going to get started in about 2 minutes. 2 minutes. All right, folks, hope everyone enjoyed their lunch. Next up, we have Saurabh Bajaj from Lyft, who's going to talk about Kubernetes. And I run a Mesos shop, but he says he's going to convince us to switch. So we'll see.
How's everyone doing after lunch? Thanks for attending this talk. My name is Saurabh. I'm an engineer on ML platform, machine learning platform here. And today I want to speak a little bit about the technical decisions we made around building a scalable machine learning platform. I want to get started by talking about problems that we're trying to solve, and then get into some of the details of how we approach the solutions. How many people out here have used Lyft before? Just raise hands, please. Okay, so most of the audience has. And so let's talk about the classic Lyft experience. You open your app, you're trying to put your pickup spot and destination, select a payment method, and call a ride. When this process, underlying this process, there's a lot of machine learning that's happening. We can smartly pick the from a very noisy GPS data to know exactly where you might be. Then we can also do some predictions on what are the most likely destinations you want to go to, based on your ride history, based on your previous ride you took. We might be able to pick automatically a payment method if you have several of those. Maybe use a different card during commute hours compared to a business trip that you're on, or during weekend rides. We can run machine learning models to optimize what driver gets dispatched to, or predicting the ETA of your ride from your source to destination, or picking up the right matching passengers if you're taking a shared ride. So every part of the experience has machine learning powering it. We have hundreds of machine learning researchers working on just the classic Lyft experience. Aside from that, we have a ton of people working on autonomous driving, using deep learning extensively for computer vision, planning, and mapping. So my team's job is to build out a machine learning platform that makes it easy to develop new models, prototype many different approaches, to your machine learning model. Once you have a few models that you've selected, we want to make it easy for you to try out different training algorithms. For example, if you might want to tweak the learning rate on your model and try out different learning rates, try out different optimizers. How can we make it easy to scale out one model that you've developed and run many executions of those with different hyperparameters? Once you have a model that performs the best, we also make it easy for you to ship that into production. There are different paths to production. For a model that runs during the web request for serving a ride, it needs to be served as a web service. Other models may do some kind of offline prediction on a daily basis or on a weekly basis. For example, figuring out the right population to send out an incentive to. There is a third type of inference, which might be a machine learning model running on the edge, for example, an autonomous car. So how can we make it easy across all these different types of deployments for a research scientist to go through this life cycle of model development, training, and production? So research scientists spend a lot of time doing non-modeling tasks today. If the audience is full of people who are building their own models, you might realize you spend a lot of time collecting the right data set, querying it, filtering it, slice and dice it to generate the correct training data. And then if you're training really compute-intensive models like deep learning models, you need to be able to provision the right hardware for your model. You might want to run many different iterations of those models. You need good logging and monitoring. And our team's job is to make all of that simple. So I'm going to get into some of those requirements to start. We wanted to build a system that's framework agnostic. The current landscape of machine learning is so rapidly changing. There are some really great frameworks like TensorFlow, PyTorch that have come up in the last few years. And then there is the whole scikit-learn ecosystem, or boosted trees, any new libraries that might come up. So we want to support any arbitrary framework and not be tied into an implementation for a specific framework. Support for GPU workloads. Almost all deep learning models are extremely compute intensive, several orders of magnitudes more than traditional machine learning approaches. And we want to serve those internal customers to it who are training very large scale models that feed imagery or video data and can have model training that can run for days. How can we make their job easier and support single GPU, multi-GPU, or distributed training workloads? We wanted the system to be cloud agnostic. And the main reason for that is, along with the software ecosystem, the hardware ecosystem for machine learning is also rapidly evolving. A study by OpenAI shows there's almost a 10x improvement year over year in ML compute performance, which is extremely fast. And there are custom accelerators, ASIC-based model training systems that are being developed. NVIDIA has the Volta GPU, which is the current state-of-the-art GPU for model training. However, Google's working on TPU chips that are custom ASICs built for model training. And we wanted to be able to leverage any of this hardware because we cannot anticipate exactly how this ecosystem is going to move. So we wanted to be cloud agnostic. Now, with a lot of power comes a lot of responsibilities, right? However, we have many levels of users. We have researchers who come from an academic background and don't really want to deal with a lot of infrastructure problems. They don't want to get into the nitty-gritties of how certain infrastructure is set up to launch their jobs. However, for some advanced use cases such as distributed training, or if you want to build custom ops for your TensorFlow model, we also have very advanced program software engineer users who want to get the maximum flexibility around defining their models. So we wanted to support both such use cases. So we decided to use Docker containers as our primary abstraction for most of our jobs. This solved a lot of problems around dependency management. It makes it easy to be framework agnostic. As long as you can package your code into a Docker image, you can run it on our system. Now, with containers, we need to decide a good execution engine for those containers, and the Kubernetes ecosystem has really blown up in the last few years. Kubernetes provides a very rich set of APIs for launching very complex workloads. You can scale out very easily using Kubernetes on any of the cloud providers. It provides a cloud agnostic API for us to launch jobs, which can then translate from either AWS to Google Cloud to any custom deployments. It handles a lot of different infrastructure challenges that we would have to design on our own, for example, and I'll get into some of the details. One of the challenges of using Kubernetes, however, is its power. It is very complex. There's very low-level APIs that most users may not want to deal with. So I'll show how we create the right abstractions to help our users launch all kinds of workloads. We decided to go the route of providing an easy path that is fully UI-based. So we have our own UI-based system. Internally, we call it lift-learn, that allows a data scientist to go from developing in Jupyter notebooks to containerizing their models to running very large-scale hyperparameter search and then deployments. However, for advanced users, we provide a much lower-level API using command line to give them full flexibility for defining their machine learning workloads. So let's go through some of those features. Notebooks. This is the entry point to any researcher's machine learning development flow. You want to have an interactive environment where you can easily query data sets, build out different stages of your model development, and try it out. And Jupyter is the de facto standard right now for a lot of these model developments. So this is lift-learn. On the left side, you see the different functionality we provide. And the first functionality is environments, which are Jupyter environments for developing either Python or R models. We are moving quickly towards Python as our standard programming language for most workloads, just because it provides us really great end-to-end integration from development to productionizing. So in this environment, I can quickly pick a software environment that I would like to launch. So we provide some pre-baked software environments. Here you can see I have 4 different environments. One, which is the standard Docker image containing most of my commonly used Python libraries. And next to it is a deep learning plus TensorBoard image. In the standard image, we only launch a Jupyter notebook. However, with the deep learning image, we can launch both notebooks as well as TensorBoard. TensorBoard is a visualization tool that TensorFlow and our PyTorch use for measuring your learning performance over time. Similarly, we allow different teams within Lyft to provide their own software environments in the form of Docker images. So if you care about a certain set of requirements, which are different from most users, and you want to pin different versions of scikit-learn or use a RC branch or TensorFlow, you can do that and provide that as a custom environment right here. Next, you pick the hardware resources you want to run this job on. So we provide some pre-configured hardware environments. You can choose many different configurations of CPU, memory, and GPU that you would like for your job, for your notebooks. Having some fixed environment choices makes it easy for users to quickly go through this flow. However, you can use the command line tools to arbitrarily create any kind of environment, which translates to Kubernetes resources behind the API. So you click next, and now you have a new environment set up for you. Now you can see we already provide a link to the notebook right there in the UI. You click on it, and it'll take you to your Jupyter environment, where you can start developing your models. In the background, these are some of the links that are available to you once you launch the job. You have the notebook interface where you can develop any model, and you have the tensor board for visualizing any model training that you might be running on it. In the background, we're creating Kubernetes objects. The primary one being a pod. Pods are the lowest execution units inside Kubernetes. And you can configure many different containers to run inside a pod. So here we're launching a pod with a given set of Python requirements, along with the right resource requests that the user submitted. It picks up a certain image, but you can using it as a Docker image gives you full flexibility to pick the image you would like to run. Along with the pod, we attach certain volumes. A volume can represent either a temporary disk space the user might want for loading some data sets or generating some training artifacts, such as checkpoints, intermediate checkpoints for your models. We also mount NFS into these pods. So we have AWS EFS, which we mount as a persistent volume on each notebook. The primary use case there is a user can just start a new notebook, start developing a new model, save their notebooks on the EFS, and once you're done, you can terminate the environments, come back again next day and start where you left off. So it makes good use of the resources by letting you checkpoint all your work and come back to it later, at a later point. We also provide GitHub-based integration. So let's say you've done all your iteration and now you want to push this code out for review. Then you can log into GitHub from your notebook interface directly and push it out as a new pull request or as a new commit. We also want services and ingress. These are other object types in Kubernetes, which allow you external access to any Kubernetes links. So in this case, my notebook URL is actually a Kubernetes ingress backed by Elastic Load Balancer, which allows any user to access the notebook over the internet. So what are some of the challenges we face while building this? Some of these machine learning images are extremely big in size. On average, our notebook images are between 12 to 15 gigs in size. And just downloading, because it contains CUDA drivers, it contains the whole CUDA toolkit, it has all the binaries for TensorFlow, PyTorch, supporting Python 2 and 3, and all of the frameworks that users might want. So loading a new job can become a bottleneck because it might take a long time to download these images. So what we do is we create a warm cache of images, commonly used images, on every single node on the Kubernetes cluster. That's one of our approaches for pre-caching most commonly used images directly available on every single node. This helps us eliminate half of our boot up time. Our Kubernetes clusters are also auto-scaling. So based on unfulfilled capacity, unfulfilled requests, the Kubernetes scheduler can scale up the number of AWS instances that are needed to fulfill those requests. However, that starting a new instance can take a while as well. We use Packer, which is a packaging tool, open source packaging tool for generating AWS AMIs or many other types of images. This helps us create the VM image pre-baked as is needed to launch on AWS. And it cuts down our, in the original Packer builds, it cut it down from 20 minutes to 6 minutes or so. So we combine, there's another thing we need to do, which is for notebooks, you want the experience to launch a notebook really fast. However, launching a new node can take up to 6-7 minutes. Downloading the image, if it's not pre-cached, can take 10 minutes. So we solve both of those problems. We create a warm cache of extra nodes available for both CPU and GPU types, and that's a configurable limit. So Kubernetes provides a great construct called priority classes, which we can use to create lower priority jobs that can be preempted with real workload. This allows us to specify extra capacity for jobs that are just sleeping around and they're just waiting to be preempted by real workloads. This allows us to make the notebook experience extremely fast. We're able to provide consistent notebook launch times within 10 seconds for these 15 gig images on Kubernetes. This makes the data science super productive, and that makes us happy. So remember I mentioned how your notebook code is residing on NFS. However, in order to productionize something, we don't really rely on some code lying on NFS as our main source of truth. So we provide good GitHub integration. Just from the UI, the user can go and set up their GitHub credentials. They can go to GitHub, find a token, generate a new token for their account, and register that in the credentials page. These credentials get translated to Kubernetes secret objects. The Kubernetes secret objects it's a construct in Kubernetes to allow you to store arbitrary secret data in encrypted format on the backing data store called XCD. These are encrypted at rest, and they can be mounted as part of any job that gets launched on the cluster. So once you set up your GitHub token, once you set up your Hive credentials, once you set up your Presto credentials, then we make them automatically available on your container during any notebook or training job creation. So you can access external data source for retrieving your training data sets. And the same way, the credentials are used for publishing new code into GitHub. So GitHub token is a form of credential, but access to Hive can also be another form of credential, and these are all configurable. All right, so let's talk about training and deployment. Once you've developed your model and you just want to try out many different variations of a model with different optimizers, a different learning schedule. Let's say for deep learning models, it's very common to try out different number of, it involves a lot of exploration. And we want to make the exploration really fast. And all of these jobs can run in parallel. You could launch hundreds of jobs with different learning rate or different optimizers or any other parameters, hyperparameters.